Swayam Prabha. Digital India. Educated India.
Okay, so welcome students to the next class of this course. So the last time we essentially started the new topic of statistical physics, and especially we started with the concept of statistical ensembles, right? And in the last class we actually saw that when we apply a microcanonical ensemble, which essentially means that the energy, the volume and the number of particles of a system do not change, right? So if we make mental copies of such a system equal to the number of accessible microstates. So and when we use the simple concept of number of microstates, right. So we assume that so we use the hypothesis that the equilibrium state corresponds to the state where the number of microstates is maximum, and there we saw that how the results obtained through this principle, they are in accordance with the thermodynamics, right. So essentially what we did, so we started with, so basically the way we formulated the problem was as follows. So we had a system which is insulated so that its energy does not change, its walls are fixed so that the volume does not change, and the number of particles, they also do not leak out, right. And we conceptually divided this system into two subsystems, 1 and 2, with energy E1 and E2, and corresponding number of microstates omega 1, which is a function of E1, and omega 2 on the second subsystem, which is a function of E2, right. And essentially we saw the condition, there were three conditions for equilibrium depending upon which parameter we relax, right. So we saw that for thermal equilibrium, so the condition was as follows. So the partial derivative of log of omega 1 is equal to partial with respect to E1 is equal to partial derivative of log of omega 2 with respect to E2, that was equal to 1 divided by kBT, right. So essentially okay, so essentially the condition was this, right. So this is the condition for thermal equilibrium, and for mechanical equilibrium, so we saw the partial derivative of the same quantity log of omega 1 now with respect to volume V1 should be equal to the partial derivative of log of omega 2 with respect to V2, and for diffusive equilibrium, the condition was the partial derivative of log of omega 1 with respect to the number of particles, that should be equal, right, between both these subsystems, all right. And we also realized in all these three equations there is a quantity which is log of number of microstates, right. It appears over and over again, right. And later on we like we saw earlier in the course as well, so we realized that this quantity can be conveniently expressed as the entropy, right. So if we define basically log of omega 1, basically kb times log of omega 1 to be S, which is the entropy, okay. So then we can see that these results are in accordance with the thermodynamics, right. So essentially So we saw that from in thermodynamics, especially from the first law, we can write our first law as follows. So this is ds equals dE divided by T plus P by T dV minus mu by T dN, and here we can see that the quantity which is del S by del E, like I have written here, right. So what I am saying is this can be okay. So this is at fixed volume and N. Similarly, P by T is del S by del V at fixed E and N, E and N, and similarly minus mu by T is the partial derivative of entropy with respect to N at fixed E and V, right. And if we essentially substitute the value of S from this definition as Kb times log of omega, right. So, does not need to write 1. So, if we substitute this, so we can actually define the definition from statistical mechanics. We can write the partial derivative of this quantity del log of omega with respect to energy is basically 1 by Kb T, right. Similarly, from here we can write a partial derivative of log of omega with respect to volume is P by Kb T, and similarly from here we can write the partial derivative of log of omega with respect to number is negative of mu by Kb T, right. So, we saw that how from statistical mechanics we get the same results as we expect from thermodynamics, right. So, that is what we did in the last class, and towards in the second half, now remember, in order to get these conditions for equilibrium, we basically maximized the quantity which was the number of microstates, right. And later on we asked this question, okay, so if the system tends towards the maximum of this number, so how sharp is that? So what is the functional form of that quantity, right. So that which we defined as multiplicity function, right. So corresponding to that equilibrium state, how many microstates are there, right. And we basically took a very simple example of coin tossing, right. So the way we formulated it was, so we have n number of coins, and we know that the most likely outcome of tossing these coins independently would be getting n by 2 heads and n by 2 tails, right. And later on we asked, okay, so what is the probability of getting slightly less than n by 2 heads and slightly greater than n by 2 tails. So how does this function, how does the number of likelihood or the number of microstates corresponding to that particular event changes as a function of deviation from the most likely event, all right. So essentially we defined a multiplicity function, right. So which is g of n and s, and we saw that this is n factorial divided by n by 2 plus s factorial and n by 2 minus s factorial, right. And we know that so this function achieves its maximum value for s equal to 0, right. So because for s equal to 0, that corresponds to the outcome that half the coins are showing heads and half the coins are showing tail. So essentially if I plot this function as a function of s, so this is g, so we expect this function to have a peak at s equal to 0, right. So it will attain its maximum value at s equal to 0, and in the last class we saw that the functional form of this function is a Gaussian, which can be written as follows. So g of ns is g of n0 times exponential of minus 2 s squared divided by n, right, where we saw that the quantity log of g of n0 is equal to half log 2 pi n plus n log 2, right. Or if I or I can write it as follows. So if I take exponential on both sides, So, g of n0 becomes exponential of, okay, so I can just maybe simplify this a little bit. So, log of, so I can take this there. So, this becomes log of 2 by pi n half, and this is 2 raised to the power n. So, I can multiply this by 2 raised to the power n, and I can write it as follows. So, this is 2 by pi n raised to the power half times 2 raised to the power n, right. And this quantity must be an approximate form of must be approximately equal to n by 2 factorial times n by 2 factorial, right. So, remember, in order to evaluate this, we use the Stirling's approximation, and we get the simplified form which looks like this, all right. Okay, so that the value of this function at s equal to 0 is basically equal to g of n 0, right. So, now let us ask another question, right. So, consider that we deviate a little bit from this function, right, such that okay, so let us evaluate the value of this function. Okay, so okay, so consider a deviation in s by amount 1 n divided by 2 square root, right. So, so what I am saying is, so plus minus, right. So, let us move from s equal to 0 by an amount plus square root of n by 2 and minus square root of n by 2 on both sides, right. So, say we move here and move here, sorry, and move here, okay, and this corresponds to minus n by 2, and this corresponds to plus n by 2, okay. And if I now plug this value of s back into this equation, right. So, I will get, so you can see if I put s equals n by 2 here, so s squared will be n divided by 2, and we will get e raised to the power minus 1, right. So, in that case we can write g of n s, which is equal to okay, so I can just write, so s equals to g of n 0 divided by e, right, because we got e raised to the power minus 1, okay. So, that means if I deviate my s by an amount minus square root of n by 2 and plus square root of n by 2 on either side of s equal to 0. So, my value of this multiplicity function becomes g by e, right, where g corresponds to g of n 0, okay. Then we can define another quantity which is known as fractional width, right. So, what will be the fractional width? So, fractional width of this function, of multiplicity function. Okay. So, that will become, okay. So, the way we define the fractional width is as follows. So, what is the width of this distribution with respect to the number n, right. So, the deviation, so this is like s divided by n, and now if I substitute the value of s, which is now square root of n by 2, right. So, this becomes square root of n by 2 times n, which I can write n squared inside the square root, and this becomes 1 by square root of n, right. So, that means if I continue to increase the number of coins in my problem, right, or number of molecules, or in this particular case number of coins, so that this distribution will continue to become thinner and thinner with respect to n, right. So, you can see that this fractional width goes as 1 by square root of n, and it approaches 0 as n goes to infinity, right. So, as we increase the number of coins in our problem, so this function becomes thinner and thinner, right, and it becomes sharper and sharper. And if I can like draw it in a certain way, so this is s equal to 0, and so this function takes like various forms. So, this is like this is a typical, sorry, so this is a typical form of this function, which is a Gaussian. Okay. But if I now decrease the number of particles, for instance, So, this function becomes broader, all right. But if I now increase the number of particles, so this the thickness of this function becomes, so this functions become very thin, right, it becomes super sharp while maintaining s equal to 0, while staying while showing a peak at s equal to 0, right. So, this function, so this is the direction in which we are decreasing increasing the number of particles, right. So, n increasing, right. So, basically if I write n1 which is yellow and n2 which is black, okay, so I can write here n2 and n3. So, here basically what I am saying is n3 is greater than n2 is greater than n1, all right. So, n1 corresponds to the blue the yellow line, the n2 corresponds to the black line, and n3 corresponds to the red line, right. And if you have a large number of particles in your system, so this multiplicity function continues to grow, right, it continues to become sharper and sharper, all right, which means the deviations from the mean become rarer and rarer, right. So, it becomes highly unlikely for your system to be showing a value which is away from s equal to 0, right. So, it is like saying if I toss 10 coins, there is more likelihood of getting 700 coins 7 coins to be facing head and 3 coins to be facing tail. But now if I toss 1 lakh coins, right, so it's very unlikely to get 70,000 heads and 30,000 tails, right. All right. So, okay, so let us now again basically move now what we will do is we will now apply this concept to a microcanonical ensemble, right. So, let us go back to microcanonical ensemble. All right. Okay. So, again so essentially the way we okay, so the way we defined set up the microcanonical was as follows. So, we had a system, right, which we insulated and we divided it between two subsystems, subsystem 1 and subsystem 2, and we assumed that the energy of subsystem 1 is E1 and energy of subsystem 2 is E2, and corresponding number of microstates is omega 1 and corresponding number of microstates is omega 2, all right. Okay. So, now let us define a quantity, right. Okay. And also we assumed that E, which is E1 plus E2 is fixed, right, N is fixed, N and V are also fixed, and corresponding to the total internal energy E of this system, there are sigma total number of microstates in this system, all right. Okay. So, now let us define a quantity. So, define P of E1 which is the probability to find subsystem 1 to be subsystem 1 to have energy E1, right. And this can be written as follows. So, this is like basically the number of microstates in subsystem 1 in 1 I can just write 1 that correspond to energy E1 times the same thing number of microstates into that corresponds to energy E2. So, remember E2 is E minus E1 divided by the total number of accessible microstates, all right. So, this is how we can define this probability. So, in other words, this can be written as omega 1 E1 times omega 2 E2 divided by omega total of E, all right. And there is an underlying assumption which goes here, is that all the microstates are equally likely, all right, equally likely. Okay, it's equally likely to for this system to exist in any of these microstates, right. And the other thing which I want to mention is like the quantity omega 1 E1, right, or omega 2 E2. So, what is this quantity? So, remember when we were tossing the coins, we saw that this quantity is essentially the multiplicity function, and it grows as it has a fact, it grows as 2 raised to the power n, right, where 2 is the, like this was the coin tossing experiment where there were only 2 likelihoods in the experiment, either it was heads or tails, but still the number of outcomes, possible outcomes, that grew as a function of 2 raised to the power n, right. Similarly, for any thermodynamic system, it is not really a coin tossing, but thermodynamic systems have certain energy, right, and corresponding to that energy scales, you can have various microstates, right. So, that energy can translate to various positions and momenta in the phase space, right. So, therefore, in that analogy, so we can see that the quantity omega of E in general, that scales like e raised to the power n for n number of particles, n number of molecules. Okay. So, this is a huge number, right. So, typically we are dealing with the number of particles as high as Avogadro's number, and of course, energy is also very high at high temperatures, right. So, therefore, the number of microstates that we are dealing with is a very high number, and we also saw it in one of the examples that we took when we heated 1 gram of water by 0.0001 degree Celsius, right. So, there we got a number which was like exponential e raised to the power 10 raised to the power 17, right. So, these are huge numbers that we are dealing with, all right. So, therefore, it is always like convenient to work with log of these quantities rather than omega alone, all right. So, we will come back to that, but since this number is very large, right, we can, and we also know that E2 equals E minus E1, right, provided for large n and short range interactions, right. This is what we did in the last class, right. So, if the interactions are short ranged and the system size is very large, there are large number of molecules in the system, we can ignore the molecules that are like sitting at the boundaries of subsystem 1 and 2 and interacting with each other, right. So, that we can with very high confidence we can write E2 equals E minus E1, all right. So, therefore, correspondingly we can also claim that the number of microstates corresponding to energy E1 is omega 1 E1, and number of microstates corresponding to energy E2 can be written as omega 2, which is now E minus E1, right. So, essentially if I increase my E1, the E2 will go down since the total energy of this system is conserved, all right. Okay. So, like I just mentioned that that this function which is the number of microstates that grows as e raised to the power n, right. So, therefore, I can with confidence say that the number of microstates corresponding to subsystem 1 which is omega 1 E1, that is a rapidly increasing function of E1. So, similarly, I can also write omega 2 which is now E minus E1 is a rapidly increasing function of E minus E1, right. But since E is a conserved quantity, right. So, if I increase E1, so this will go down, or I can write it is a rapidly decreasing function of E1, right. So, if the number of microstates in E1 grows, then the number of corresponding number of microstates in subsystem 2 will go down, right, because the total energy is conserved, all right. So, therefore, remember the quantity of interest here is P of E1, right. So, we are trying to calculate the probability for this subsystem E to exist in energy state E1, and this is a product of omega 1 E1. Okay. So, I can write my P of E1. So, P of E1 is basically omega 1 E1 times omega 2 of E minus E1. Okay. So, this is omega 2, and of course, there is omega total E, which is a constant, right. So, this is a constant, and if I plot this, so this is my P of E1, right. So, this is product of two functions. One function is rapidly increasing with E1 and other function is rapidly decreasing with E1, right. So, one function increases rapidly and the other function decreases rapidly, right. So, this is my omega 1 E1, right, and this the decaying function is my omega 2 E minus E1, right. And the product of these two, one decreasing and other one increasing and other decreasing function has to have a maximum, right. So, therefore, the resulting the result of these two products is looks something like that. So, it achieves its maximum value when both are like large and finite. Okay. So, remember the x axis here is E1, right. So, if I go to very large E1, right. So, even though omega 1 of E1 will be very large number, but omega 2 E2 will be almost 0, right. So, therefore, there will be a so this red so this product will be small, and similarly on the other extreme, right. So, if my E1 is small, omega 1 of E1 will be very small, right. So, therefore, it will be 0. So, there will be an optimum value of E1, which we can define as E1 bar, okay, which is the average value. Okay. So, this is E1 average. Okay. So, this is E1 average, all right. Okay. So, therefore, now like I said, it is always convenient to work with logs of these functions, right. So, let us take log on both sides. Okay. So, we can write this as follows. So, this is log of P of E1 equals log of omega 1 E1 plus log of omega 2 E minus E1 minus log of omega total of E, and this is a constant number, right. So, this is a constant, okay, which we do not have to worry about. All right. Now, our aim is to basically Taylor expand this function around E equals E1 average, right. So, basically performing Taylor expansion around E1 equals E1 average, all right. So, I can write my log of P of E1 close to E1 average to be equal to log of P of E1 computed at E equals E1 average plus E minus E1 average of partial derivative of log of P E1 with respect to E1 computed at E1 equals E1 average plus 1 by 2 factorial of E1 minus E1 average square, the double partial derivative of log of P of E1 with respect to plus so on, right, and there are higher order terms. Okay. So, which we can ignore, right. So, because we are considering the deviations to be very small, all right. Okay. So, okay, so clearly, so at E1 equals E1 average. Okay. So, what is the partial derivative of log of PE1 with respect to E1, right? So, clearly it achieves a maximum, right. So, therefore, this quantity is 0. Okay. So, del log of P of E1 is 0, and also it's another derivative, double derivative. Okay, so this is, remember, this is a E1 bar. So this is at E1 bar. So this is positive because P of E1 bar is a maximum. Okay. So therefore, we can write our final result, and we can ignore this term, right. So okay, so and we can ignore all the and also we can ignore all the higher order terms, right. So therefore, I can write my final result as follows. So my probability for a system, a subsystem 1 to exist in any energy state E1 is equal to probability of its value at E1 average, right. So, I am just substituting that times exponential of, okay. So, another thing, we can assume that this quantity is some number 2k, okay, which is some constant, all right. So, okay, so assuming that this is some, okay, so this is 2k. So, if I now put this 2k here, so the 2 and 2 will cancel out, and I will get exponential of minus k times E1 minus E1 average whole squared. Okay. And again you can see that this function looks very similar to what we got for in the case of coin tossing, right. So, there also we had an exponential of s squared divided by n, right. So, here the role of s is played by the deviations of the energy from the average. So, remember what was s? S was deviation from equal number of heads and equal number of tails, and here the deviation is from some average energy which subsystem 1 will have, right. And so, what I am saying is this is also a Gaussian distribution. Gaussian distribution sharply peaked at E equals E1 average, E1 equals E1 averaged, all right. So, this is a Gaussian distribution, and yeah, so there is a small mistake that I did. So, this should be less than 0 because it is a maximum. So, second derivative is negative. So, and what we can do is we can equate it to equals minus 2k, where k now is a positive number, right, which ensures that this second derivative is a negative number, and that is the distribution that we get. Okay. So, I can like very easily draw it. So, this is P of E1, and it has a well defined peak at E1 average, and it is a very sharp distribution because the energy of the system is very high and the number of particles is Avogadro, and right, we can now see that as we increase the number of molecules in the system, the sharpness of this function also increases, all right. All right, and like I said, so since E1 and E1 average and n are very large numbers, deviations from E1 average are extremely rare. Okay. So, the number of microstates corresponding to the average energy is so high that any deviations from E1 average become exponentially rarer and rarer, all right. So, therefore, in a micro-canonical ensemble, the energy of the system is fixed, and any fluctuations from that average energy are very small. Okay. So, this is the main outcome of the main property of this microcanonical ensemble. All right. So now let us do a transition from microcanonical ensemble to canonical ensemble, and we will then like compare these two ensembles again. Okay, so microcanonical to canonical transition. Sorry, not transition. Ensemble. Okay. So how do we go about it? All right. So now, so remember in the last part, like in microcanonical ensemble, so we divided this this system into two subsystems which were almost equal to each other, right. So I drew a line in the middle, which means the size of subsystem 1 is almost equal to size of subsystem 2. Now we will go to an extreme limit, right. So let us assume that subsystem 1, okay. So remember I am still in a microcanonical ensemble. So this my total system is still isolated, okay. So this system is still isolated, insulated, it does not exchange heat with its surroundings, it has rigid walls and the particles do not leak out, right. So, so in this system the total E and V is still fixed, right. But the difference that I am making now is, so my subsystem E1, right, or the subsystem 1, the subsystem 1 with energy E1 and microstates omega 1, I can omega 1, and there is a subsystem 2 with energy E2 and microstates omega 2, okay. And the assumption that I am making is, so so take the limit E1 much smaller than E2, all right. So earlier my E1 and E2 were comparable to each other in microcanonical, but now let us work, let us do the same calculation, but now E1 is much smaller than E2, okay. So instead it is like so small that I can just write this to be the subsystem to have energy epsilon and number of microstates omega of epsilon, and my subsystem 2 has an energy E minus epsilon. So remember total energy is still constant and number of microstates omega E minus epsilon, all right. Okay, and we are assuming so epsilon is much smaller than E minus epsilon, okay. So the energy of subsystem 2 is much greater than energy of subsystem 1, okay. So in this case again we can now define what is the probability for this subsystem 1, which is now very small, to exist, to have an energy value epsilon, okay. So in this case P of epsilon will again be equal to number of microstates. So in this case I can write my P of epsilon as follows. So this is omega epsilon times omega E minus epsilon divided by the total number of microstates for a system which has energy E, all right. So and and again I can take log on both sides. So log of P of epsilon becomes log of omega epsilon plus log of omega E minus epsilon minus log omega total of E, all right. And again this is a constant which we can conveniently drop, right. Okay. So now now remember since epsilon is much smaller than E minus epsilon, we can also assume that the corresponding number of microstates will also be small, right. So omega epsilon will also be much smaller than omega E minus epsilon, all right. So therefore I can basically drop this out, right, and I can just write my log of P of epsilon to be equal to log of omega E minus epsilon, all right. Okay. So, again we can now Taylor expand. Okay. So, let us do Taylor expansion. So, Taylor expand around epsilon equal to 0, right. So, we are assuming that epsilon is so small that it is now peaked at 0, right. So, since it is very small, so we can assume epsilon to be, so we can Taylor expand this function around epsilon equal to 0. Okay. So, therefore, so the log of p of epsilon can be written as log of omega e minus epsilon, right, computed at epsilon equal to 0 plus plus e minus epsilon minus e times partial derivative with respect to energy E of this quantity omega E minus epsilon computed at epsilon equal to 0 plus the higher order term 1 by 2 factorial E minus epsilon minus E squared, again computed at epsilon equal to 0 plus higher order terms, right. And this cancels out. So, we have an omega term and here we will have an omega squared term, right. But since we are expanding around epsilon equal to 0, we can drop this term out, right. So, we can drop this out for small epsilon and we can just stay with the first term, and this basically just becomes log of. So, at epsilon equal to 0, this is just omega E minus, so this cancels out. So, minus epsilon times partial derivative of log omega E, right, plus all the higher order neglected terms, all right. Okay. So, therefore, okay. So, now let us use our result from the microcanonical ensemble, right. So, from microcanonical ensemble, right. So, we saw that the quantity partial derivative of log of omega with respect to energy is basically the definition of temperature, right. So, this is 1 by kBT and this is sometimes also denoted by a symbol beta, which is known as Boltzmann factor. Okay. So, let us just substitute the del by del E of log omega E with 1 by kBT or beta. So, I can write my final result, which is as follows. So, therefore, log of P of omega becomes log omega E minus epsilon divided by kBT, all right. And if I now take exponential on both sides, so this becomes P of epsilon equals omega E raised to the power minus beta epsilon, right. So, like I said, beta is 1 divided by kBT. Okay. All right. And since the total energy of this system is fixed, right, it is still a microcanonical ensemble in that sense. So, this is a constant. Okay. But more importantly, now we can plot this function, right. So, if I now plot my P of epsilon as a function of epsilon. So, this is an exponentially decaying function, right. So, it is constant times e raised to the power minus beta. So, at a constant temperature, this is a exponentially decaying function, all right. So, I can see that this function decays exponentially, all right, and this is the result for canonical, right, and this is a so this is decays like e raised to the power minus beta epsilon. But now let us compare it with microcanonical, right. So, remember in microcanonical we saw that the system has a well defined average value E1 average and fluctuations around it are very rare, right. So, if I draw the microcanonical on the same graph, so it was a sharply peaked Gaussian function, right. So, let me do it. Okay, so this is the microcanonical with a well defined average energy E1 average, and this is microcanonical. And here the functional form, okay, so here we saw P of E1 was exponential of minus k E1 minus E1 bar squared. Okay. So, this is the main difference, right. So, now basically what I am saying is, in the limit, if my subsystem is much smaller than the other subsystem, so so there are huge deviations, huge fluctuations in its energy, right. It does not have any average energy, its energy falls exponentially, right. And the probability that this system can be found at any energy value epsilon will be decided by the temperature of the subsystem 2, right, and the number of microstates that are present in subsystem 2, right. So, it is like subsystem 2 is controlling the physical state of subsystem 1. However, in microcanonical ensemble, since both the systems were almost equal to each other, right, so their dimensions were equal to each other, the subsystem 1 saw very rare, very almost zero fluctuations of its average energy, but in this case the energy fluctuates a lot, all right. So, essentially so the main result is that, so if our E1 is much smaller than E2 in a microcanonical ensemble, so subsystem 1 becomes a canonical ensemble. Okay. And the energy state in which that particular subsystem will exist will be decided by the properties of the subsystem 2, which is in contact with subsystem 1, all right. All right. So, there is okay. So, that is one result, but there is another very inconvenient thing which has happened, is that in order to evaluate the probability or the state of the system in which we are interested in, for example, subsystem 1, we have to compute the number of microstates in a subsystem 2, right, in the reservoir. For example, if I take my cup of coffee and keep it in the window, right. So, at any given point its energy will be decided by the atmosphere, right, and if I want to compute the probability that what is the energy state of the coffee, I have to basically evaluate all the microstates of the atmosphere, right, which is not really convenient. All right. So, there is another way to basically come out of that problem, right. So, let us assume, okay. So, say our okay. So, now the picture is as follows. So, we have a subsystem 1 which is in contact with a huge, now we can call it reservoir, right. So, this is the subsystem 1 epsilon, right, and it is in contact with another subsystem which has energy E minus epsilon, which is almost equal to E, and it is at certain temperature T, right. And say there are various multiple energy levels which are possible in subsystem 1, right. So, if there are multiple energy states in our system, right, say there are epsilon 1, epsilon 2 and so on, right. So, in that case we can very easily see that the probability to be in energy state 1 plus probability to be in energy state 2 plus so on. So, the sum has to add up to 1, right. So, this is just the sum of all the probabilities has to be 1, all right. But what I can also write is that the probability to exist in any state, say epsilon 1, is basically equal to, so this quantity, right, omega e, right, which is unknown, right, times exponential of minus beta epsilon 1 divided by all the other energy states, right, omega e, which is the common factor, minus beta epsilon 1 plus e raised to the power minus beta epsilon 2 plus so on, right. And if we define the probability in such a way, so this inconvenient factor like drops out, right. It is a common factor which cancels out, and we are basically left with much better looking result, which is minus beta epsilon I divided by summation j e raised to the power minus beta epsilon j, and in fact there is a name for it. So, this denominator is denoted by z, where z is known as canonical partition function. Okay, so, this is the canonical partition function, and it provides a convenient way to compute the probability that a system exists in any energy state epsilon, all right. So, therefore, we now do not really have to worry about what is going on in the reservoir, right. We do not really have to compute the number of energy states or in a number of microstates in the huge reservoir, all right. So, okay. So, now it might happen that there are degeneracies in this system, right. So, for example, so like I drew energy states, various energy states epsilon 1, so epsilon 1, epsilon 2 and so on, epsilon 3 and so on. So, it is possible that there are multiple levels which have the same energy, right. So, there can be degeneracy. So, there are so G1 number of states with the same energy, G2 number of states with the same energy and so on, right. So, in this case we can modify our partition function. So, basically this partition function, which for non-degenerate case was just summation e raised to the power minus beta epsilon j. So, now in case of so for degenerate energy levels, okay. So, I can write my canonical partition function as follows. So, z canonical can be written as summation g j e raised to the power minus beta epsilon j, okay. So, this is another way to represent canonical partition function, okay. So, this is also an important result. And it might also happen that that energy scales are not really quantized, they are not discrete, they are uniform like continuous energy states, in which case we can basically, so say this is the energy, right. So, this is the energy axis, okay, and system can exist in all these energy values, right, in which case we can define the quantity that we basically derived, which is the density of states, right. Okay. So, say we look at a tiny interval d epsilon, and there is a term which is density of states at that particular energy E epsilon, right. So, in which case, so for continuous energy levels, okay. So, we can define our canonical partition function as integral 0 to infinity of d epsilon, which is the energy the density of states, times e raised to the power minus beta epsilon d epsilon, where d epsilon is the density of states, okay. So, that is where I will end my lecture. So, see you in the next one. Thank you.